Okay, so in the last two videos, we have been looking at linear growth and decay. And in terms of financial applications, that involved loans and investments earning simple interest and flat rate or unit cost depreciation. So what we want to look at over the next two videos, actually over the next three videos, is specific examples where we have geometric growth and decay. So geometric growth and decay are when we have recurrence relations of this form, so where we multiply by something each from one term to the next. So, for example, on the left hand of this table here, we've got geometric growth, and we get geometric growth if the thing that we're multiplying by is bigger than 1. Okay, so here if we have a sequence where the starting value is 1, and to get from one term to the next we multiply by 2, so we're doubling every time, we're going to get geometric growth. If we double something every time, it clearly gets bigger and bigger. Now the other thing to note is if we were to plot the points of this sequence on a graph, is it doesn't get bigger in a linear fashion like we saw previously. It gets bigger in an exponential fashion. So if you start off with 1 and you double it, you get to 2, and you double that, you get to 4, and you double that, you get to 8, and then you get to 16, then you get to 32, and then you get to 64. So, the first step is just going up by 1, but the next step's going up by 2, the next step goes up by 4, the next step goes up by 8, then we go up by 16, then we go up by 32, next we're going to go up by 64. So we get this exponential growth, okay? We've seen a lot of that lately with all sorts of COVID graphs. Geometric decay would be the same thing when we're multiplying by something each time, but when the number that we're multiplying by is between 0 and 1, so if it's a fraction. So if we, for example, in this particular example, we start with 64 and we multiply by 0.25, so we take a quarter every time. Okay, so then what will happen if we take 64 and multiply it by 0.25, it becomes 16, and multiply that by 0.25, it becomes 4, multiply that by 0.25, it becomes 1, then we've got 1 quarter, 1/16, so we get smaller and smaller and smaller, but not in a linear fashion, in an exponential fashion when we have geometric decay. Okay, so we see these kind of sequences when we are dealing with compound interest problems. So we want to have a look at compound interest in this video, and the depreciation equivalent is reducing balance depreciation. So we'll also have a look at that. So compound interest means that the interest is calculated not based on the principal value, but based on the value of the loan at the time. Okay, so this means that as the value of the loan or investment increases, a larger amount of interest is being paid or earned. And the value of the loan or investment earning compound interest exhibits geometric growth or exponential growth. Okay, so for example, let's consider an investment of $100 at 10% per annum compound interest. Now, two videos ago when we were looking at linear growth and simple interest, we did an investment that was $100 at 10% per annum simple interest. And it would be worth perhaps flicking back in your notes to have a look at the difference in the numbers. So basically, if it's compound interest, it means that the investment increases by 10% of its value in the previous year. So every year it increases by 10%, not 10% of the original value, 10% of the current value. Okay. So when we increase something by 10%, we're finding 110% of the original amount. Okay. If we're increasing by 10%, we've still got the original 100% plus an additional 10%. So we now have 110% of what we originally had. So if we want to find the value after 1 year, we're finding 110% of the value at the beginning, which was the principal amount. 110% is 110 on 100, so that's 1.10. Okay. Hopefully we'll get better at being able to make this shift. A 10% increase is multiplying by 1.10 quite efficiently ourselves. So that means the value after 1 year is $110. So that's the same as simple interest. But then the difference is when we now look at the second year, we're not just adding on another $10, we're calculating 110% of $110. So we're increasing by 10% of $110. So the value after 2 years is 110% of the value after 1 year. That's a 10% increase. So that's 1.10 times this amount, okay? Which means we get $121. So we went up by $11 in the second year. So it's not significantly more, but we see that only compounds. That's why we call it compounding interest, because essentially what happens is we're calculating interest on interest using compound interest. So if we were to continue to multiply the previous year by 1.10, so let me have a look in the CAS at generating those numbers. So we're starting with $100, press enter, we're multiplying that by 1.1. That's an increase of 10%. We multiply by 1.1 again, we get $121, which we saw in the first two calculations. Times 1.1 again, $133.10. So this time it's gone up by $12.10. Okay, so it's still not significant, but it's still going up by more than $10 every year. $146.41, so that's $13.30-ish. Okay, so every year it's just going up by that little bit more. And that's why we're not getting that linear growth when we draw the graph. We're getting that sort of exponential growth. It goes up by a bit more each year. So then after 5 years, we're at $161.05. So that's up to here on the table. 6 years, 7 years, 8 years. Okay, so we're up to $214.36 to the nearest cent. So you might remember with the simple interest amount, after 8 years, we'd simply added on $10 8 times. So we've only added on $80. Compound interest, we can see that compared to the original $100, we've added on $114.36. So it's growing more quickly, and that will only be exacerbated over a long period of time. So here what we've generated is a sequence of numbers that can be described by a recurrence relation. So if the value, Vn is the value of the investment after n years, then what we have here is that V0 is 100. So our starting value is 100. And Vn plus 1 is Vn multiplied by 1.10. Okay, we would usually write that as 1.10 times Vn. So it should be noted that in practice, this is compound interest is what is used. If you take out a loan, you put money in the bank, it's compound interest that's happening. So simple interest is a pretty not flawed, but it's fine, but it's a simplified model that's not realistically what happens. Okay, so let's formalize that into then a recurrence relation for compound interest. So if Vn is the value of the loan or investment after n compound periods, so whether that's years, months, weeks, depends how frequently we're compounding. If R is the percentage interest rate per compound period, so if it's 8% if it's per annum and it's 8% per annum, then R is 0.8. Interestingly, we'll talk about this in some examples, but if it's you'll always be given the interest rate as a per annum rate. So if you want to compound the interest monthly, you would need to divide that rate by 12 in order to then be able to use it in your formula. Okay, so the recurrence relation for the value of the loan or investment after n years is V0 is the principal amount and Vn plus 1 is capital R times Vn. And capital R, we call that the multiplying factor sometimes, is essentially if you're understanding that you're increasing by 4.8%, that is 1 plus 4.8 on 100, which is 1 plus 0.048, which is 1.048. But I want you to get better at being able to just come up with that number yourself. Okay, so for me, a 4.8% increase means I end up with 104.8% of what I started with. Percent means divide by 100, so that means I'm multiplying by 1.048. Okay, so you can use this formula if you need, and there's no reason, nothing to be said that you can't use that, but really you should be able to come up with that multiplying factor more easily than having to muck around with the formula. But it's there and it's available for you. Okay, so we're multiplying by 1.048 every year in this particular, if it was 4.8%. Okay, let's have a look at an example. So $2,200 is invested in a compound interest account with an interest rate of 4.7% per annum. Set up a recurrence relation to describe the value of the investment after n years. Okay, so V0, principal value, 2,200. Vn plus 1 is going to be, now we're multiplying, we're increasing by 4.7% every year. So for me, I would do it this way, a 4.7% in my head increase. I end up with 104.7% of what I started with. Percent means divide by 100, that is 1.047. So I'm multiplying by 1.047 every year. So to get from 1 year to the next year, I need to multiply by 1.047. As I said, if you need the formula to work out that capital R value, that's fine. So in this case, lowercase r is 4.7, capital R is 1 plus 4.7 over 100, which is 1 plus 0.047, which is 1.047. Okay, so that is utilising this rule here. Okay, use the recurrence relation to find the value of the investment after 5 years. So V5, okay, so V5, so let's set up the recurrence relation in our CAS. So we're going to have 2,200 is the principal, press enter. We're then going to multiply by 1.047 to get the value after 1 year. 2 years, 3 years, 4 years, 5 years. So $2,767 and to the nearest cent, which is the standard instruction in financial maths, 94 cents. Determine how many years it will take for the value of the investment to exceed $4,500. Okay, so let's just continue to recur our recurrence relation. So this is 5 years we're at now, so let's keep going until we get past 4,500. 6 years, 7 years, 8 years, 9, 10, 11, 12, 13, 14, 15, 16. That's our first one. So V16 is $4,587.43. So therefore it's going to take 16 years for our value, the value of our investment to go from 2,200 to more than 4,500. Okay, example 2. The following recurrence relation can be used to model the value of a compound interest loan after n years. State the principal value of the loan. Okay, so there's our principal value. That's the initial value of the sequence. So principal value, $12,000. State the annual compound interest rate. Okay, so again, we can work with a formula here, but if we understand percentage increase and decrease a bit better than that, we should be able to straight away see that this is a 6.8% increase per annum. Okay, if you can't, what you have there is that capital R is 1.068. We know that capital R is equal to 1 plus the interest rate over 100. Okay, so 1.068 equals 1 plus R over 100, and you could get your CAS to solve that equation if you need to. Okay, 1.068 equals 1 plus R over 100. Solve that for R. It will tell me that R is 6.8. Okay. But hopefully you get better at seeing that 1.068 is 106.8%, which means it's an increase of 6.8%. Okay. All right. If the loan is to be paid off in full at the end of 3 years, how much will need to be paid? So let's work out the value of the loan after 3 years. So again, let's get our CAS happening. So $12,000 is the principal, and each year we're multiplying by 1.068. Okay, so that's after 1 year, 2 years, 3 years. So after 3 years, it's worth $14,618.24, and so therefore $14,618.24 will need to be paid if we want to pay it off in full at that time. As I said earlier in the equivalent video for linear growth, this is not really realistic because you generally wouldn't allow your loan just to accumulate interest without making any repayments. So you would usually gradually pay it off by paying more than the interest each year so that it gradually comes down. We'll have a look at investigating those kind of loans when we're also making repayments and earning interest in the second half of the topic. So in the second chapter, if you're working from the Cambridge textbook. So after how many years will the value of the loan first exceed $20,000? So we can see after 3 years it's worth about 14.5. So let's continue to recur. So after 4 years, 5 years, 6 years, 7 years, 8 years. So V8, it is worth $20,311.93. So therefore, after 8 years is when it will first be worth more than $20,000. Okay, reducing balance depreciation. So reducing balance depreciation is essentially compound interest but for depreciation. So where we're going down each time. And that's going to happen, we saw right back at the beginning that happens if we're multiplying a number that's between 0 and 1 every year. So if we were to multiply by 0.9 every year, for example, the amount would be reducing each year. Whereas when we multiply by 1.1, we increase every year. So it's still the same formula, except that our R value is going to be less than 1. Again, if we need a formula here for our capital R value, our multiplying factor, this is our formula this time when we're depreciating. We're going to be decreasing by a certain percentage, so it's 1 minus that percent. Okay. As I said though, I prefer to think about it's a 10.9% decrease per year. So we're going down by 10.9%, which means if we start with 100% and take off 10.9%, we're going to be left with 89.1%. Okay, and so that is, as a decimal, percent means per 100, divide by 100, it's 0.891 would be what we'd be multiplying by every year. You would get the same value if you sub these numbers into the formula. So 1 minus 10.9 on 100, if we put that in my calculator, 1 minus 10.9 on 100 is indeed 0.891. Okay, so however you come up with that number, that's fine, but you don't have to use the formula, but you have got a formula there that will do that for you. But I'd really encourage you to try and get better at thinking about your percentage increases and decreases as being just 100 plus a value if you're increasing and 100 minus that value if you're decreasing. Okay, let's have a look at another example. The value of a computer depreciates so that its value after n years is given by the following recurrence relation. So V0 is 1950, so that's the initial value of the computer. And then each year we're multiplying by 0.82. I'm sure there'll be a question that asks us about that, but you should be thinking about what does that mean in terms of a percentage decrease. So state the purchase price of the computer. That's going to be the 1950. By what percentage does the value of the computer decrease each year? Okay, so we multiply by 82% each year, which means it is a decrease. 82% is 18% less than 100. A decrease of 18% per year. Okay, so it's about, if we're only finding 82% of last year's value, we are essentially decreasing by 18%. However, you can always take that value and the formula, and you know that 0.82 is equal to 1 minus R on 100, and you can solve that with your CAS. 0.82 equals 1 minus R on 100. Solve that for R, and it will tell you that R is 18%. Okay, so by all means use the formula, but equally I'd really encourage you to get more familiar with understanding your percentage increase and decrease as being relative to 100%. Use the recurrence relation to find the value of the computer after 3 years. Okay, so let's set up our recurrence relation here. So typing in our initial value, pressing enter, and then we're going to multiply by 0.82. So that's the value after 1 year, 2 years, 3 years. So the value after 3 years is $1,075.17. The computer will be replaced once its value falls below $500. After how many years will this occur? Okay, so we've now done 3 years, 4, 5, 6, not quite, 7. Okay, so V7 is $486.11. So therefore it will be after 7 years that we will replace the computer. It's quite a long lifespan for a computer, really. Example 4. A car costs $37,000 to buy and increases in value with reducing balance decreases in value with reducing balance depreciation of 12.5% each year. Set up a recurrence relation to describe the value of the car after n years. Okay, so V0 is going to be 37,000, and then we're going to have Vn plus 1 is something times Vn. So we need the multiplying factor that would be about reducing by 12.5%. Now I know that 12.5%, 100% minus 12.5% means that I'm left with 87.5% each year. So I'm finding 0.875 of the previous year. Remember, percent per 100 divide by 100, so 0.875. However, you could also use your formula. You know that R in depreciation is 1 minus the rate over 100. That's 1 minus 12.5 over 100, which is indeed 0.875. Just to verify, 1 minus 12.5 over 100, 0.875. Okay, use the recurrence relation to find the value of the car after 5 years. So V5 $37,000, and we're multiplying by 0.875. So that's the first year, second year, third, fourth, fifth. So after 5 years, the car is now only worth $18,977.63. The car will be written off, so essentially not worth more than the sum of its parts, when its value is less than $7,000. How long will it take for this to occur? So let's continue to recur. So we're now, that's after 5 years, so I'm going to keep pressing enter. 6 years, 7 years, 8 years, 9 years, 10, 11, 12, almost, 13. So V13 is worth $6,520.88, and so therefore after 13 years we'll write the car off. You could sell it more for parts than you could as a car. Well, that's the theory of sort of writing off. It's just not worth repairing it at that point. Okay, example 5. A photocopier purchased for $12,000 will be depreciated using the reducing balance method with an annual depreciation of 6.5%. What is the depreciation of the photocopier during the 4th year? Okay, so we haven't dealt with a question like this before, and it's really important that you think carefully about what during the 4th year means. Okay, so V0 to V1 is the first year. Okay, V1 to V2 is the second year. Okay, so that means the 4th year will be V3 to V4. So we want to work out the value after 3 years and the value after 4 years, and the difference is going to tell us how much we depreciate by. Okay. Alright, so let's set up a recurrence relation here. So we've got V0 is $12,000 for our photocopier. Vn plus 1 is, now we're depreciating by 6.5% every year. So as I said, I always do 100 minus 6.5. 100% minus 6.5% is 93.5%. So I'm ending up with 93.5% of what I had, percent 0.935. So it'd be 0.935 times Vn. If you need the formula, remember your R value is 1 minus R on 100. That is 1 minus 6.5 on 100. It's essentially the same calculation. It's just a formula that avoids you having to think about what's actually happening. So 0.935. However you get R, doesn't matter. So that's my recurrence relation. Okay, so we want to know what V3 is. So let's recur that in our CAS. So 12,000, press enter. And then we want to multiply by 0.935, which is to reduce by 6.5% once. Okay, so that's after 1 year, 2 years, 3 years. So the value of the photocopier after 3 years is $9,808.80. Okay, the value after 4 years, press enter again, is $9,171.23. Okay, and so the depreciation during the 4th year is going to be 9171.23 minus 9808.80. Now, we've got our exact numbers in our CAS here. Sorry, I did that the wrong way around. The bigger one minus the small one. We went from 9808.80 to 9171.23. So let's work out what that difference is. So we've got the numbers in our CAS. Scroll up, press enter, minus, scroll up and press enter, rounding to the nearest cent. So only round at the end. The risk that you run here is that if you round your two intermediate answers and then calculate a new answer from those rounded values and round again, that you compound that rounding error. So there's no reason for not working precisely with your CAS. Use those nice exact values and then calculate what you need. So we've reduced by $637.57. The other way that you could have thought about it is you could have worked out V3, which was this, and calculated 6.5% of that. Okay, so if we'd done V3 and then multiplied that by 0.065, that would be that's how much you've depreciated by. Okay, but one of the challenging questions here, challenging parts of this question is to understand that during the fourth year is going from V3 to V4, not from V4 to V5. Okay, so it's important that you're clear about what the fourth year is. So start from the beginning. The first year is going to be from V0 to V1, second year V1 to V2. Okay, you could keep counting right up to the fourth year, or you can then see the pattern from that point. Okay, final example here. I think it's the final one. Yes, we just want to have a look at one situation where what if we compound the interest more frequently than annually? So what if we compound the interest monthly or weekly, for example, okay, or quarterly, which would be 4 times a year. So we want to have a look at what that means in terms of what we have to do. And essentially, we have to make sure that we adjust the interest rate, okay? So let's have a look here. So we've got John invests $8,000 in an account with an interest rate of 4.8% per annum. Okay, so it's an account, it's an investment, it's going up, it's not depreciation. So we're increasing by 4.8% every year. Find the value of the investment after 1 year if the interest is compounded annually. Okay, so when we're compounding annually, N is in years in our formula. Okay. So, and then we want our interest rate to be in per annum, okay? So the interest rate is 4.8% per annum, which means that R is going to be 4.8, okay? And that means that capital R is 1 plus 4.8 over 100, which is 1.048. So that's that increase of 4.8%, okay? So we know that here our initial value is 8,000. Vn plus 1 is 1.048 times Vn. Okay, so after 1 year, that's V1. We want 8,000 times 1.048. $8,384. Okay, part B, we want to know what will the value of the investment be after 1 year if the interest is compounded quarterly. Okay, so this time it changes how you define your recurrence relation because N is going to be in quarters. So there's going to be 4 N's every year. Okay, so that means our interest rate needs to be in quarters as well. Okay, so that's 1.2% per quarter. So that means in this case, our R value, we're increasing by 1.2% every quarter, which is to multiply by 1.012. Okay. All right, so now our recurrence relation, which is where N is in quarters, is V0 is 8,000, Vn plus 1 is 1.012 times Vn, but this time if we want the value after 1 year, 1 year is 4 quarters, so that's V4 with this recurrence relation. Okay, so let's do that. We've got 8,000, we're multiplying by 1.012 once, that's after 1 quarter, 2 quarters, 3 quarters, 4 quarters. $8,390.97. So we actually see that we get a bit more money by compounding quarterly. And that's one of the key things about compound interest. The more frequently you compound, it means the more often you're calculating interest on interest. And so it grows quicker. Okay, so it's the same amount of time and it's the same annual interest rate, but by compounding every quarter rather than every year, we earn another, in this case, $6 or so. Okay, now if you extend that over a longer period of time, you earn significantly more money by compounding more regularly. So we would expect, therefore, in part C, where we're going to compound the interest monthly, that we're going to earn even more money over the course of a year. So in part C, N is in months. Okay, so it's important that we're clear about the distinction between, whilst these recurrence relations are essentially describing the same situation, they're actually not the same because we're measuring N differently. So in this case, our interest rate needs to be worked out as a monthly interest rate. So we need to divide the annual interest rate by 12, which gives us 0.4% every month. Okay, so our R value is 1 plus 0.4 over 100, which is going to be 1.004. 1 plus 0.4 over 100, 1.004. Okay, so that's a 0.4% increase every month. using the method that I do in my head, I'd be thinking I'm increasing by 0.4% every month. I'm ending up with 100.4% of what I started with. Percent means divide by 100. That's 1.004. Okay. All right, so that means that our recurrence relation in months, is V0 is still 8,000, but to get from 1 month to the next month, we're multiplying by 1.004. And so if we want to know the value after 1 year, in this case that's V12, because it's going to be 12 quarters, okay, sorry, 12 months to get to a year. So we need to, whilst it's a smaller interest rate, we're going to do it 12 times, and we should therefore end up, we actually will end up with more money because we're compounding the interest more frequently. We're calculating interest on interest 12 times, whereas we calculated interest on interest only 4 times in the previous one, and in the first one we didn't calculate any interest on interest. Okay, that's why it's growing more quickly. So let's use the recurrence relation in our CAS. So 8,000, okay, and then we're going to multiply that by 1.004, so that's 1 month. 2 months, 3 months, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we get $8,392.56. So another sort of $8.50 compared to the compared to part A, and an extra, $2 or so, just under $2 compared to part B. So just getting that sense that we can adjust the compound period, and the more frequently we compound the interest, the quicker the interest grows. So that's good for us if it's an investment. That's not so good for us if it's a loan where we're the ones paying the interest. Okay, so the work here was exercise 8E.